Hello everyone, I am Iswarya, Assistant Professor, Department of Computer Application from SFR College. Today I am going to talk about deadlock avoidance. These are our learning objectives. First, what is deadlock? Then second, next we are going to talk about deadlock avoidance. Next, these are our learning objectives. What is deadlock? Deadlock avoidance, resource allocation graph, Banker's algorithm. Okay, what is deadlock? It is a situation in which two processes are unknowingly waiting for resources that are held by each other. For example, P1, P2 are the two processes. R1, R2 are the two resources. P1 requests the resources R1, but R1 is already held by the process P2. P2 requests the resource R2, but R2 is already held by the process P1. Then both are enter into the waiting stage. There is no work progress for process P1 and P2. So it is called deadlock. Next we talk about the deadlock avoidance. The system dynamically considers every request and decides where it is safe to grant the request at a particular point. It is the one of the method of dynamically escaping from the deadlock. In this scheme, if the process requests for the resource, the avoidance algorithm checks before the allocation of the resources. If the state is safe, then the system allocates the resources to the requesting process. Otherwise, do not allocate the resources. Here we see the diagram, safe and unsafe stage of the process. Safe stage means no data will happen even they allocate the resources to requesting the process. Unsafe means the deadlock may happen if grant the resources. A safe state is not a death of a state. A deadlock stage is an unsafe stage. Here we have an example. Consider the system with 12 tap drives and 3 processes P0, P1 and P2. P0 needs 10 drives, P1 needs 4 drives and P2 needs 9 drives. Initially, P0 holds 5 drives and P1 and P2 hold 2 drives each. The system is in a safe state because P1 can finish first and releases its drives. After releasing, those resources can be used by the other processes, maintaining safety. Suppose at time T1, process P2 requests one more drive. Now, after P1 finished its execution, it have only 4 drives, which is not enough to run P0, and so it has to wait. Similarly, P2 also wait for 6 drives. Thus, deadlock may occur. This concept will be used in avoidance algorithm. Initially, the system is in the safe state. Whenever a process requests a resources, it should decide whether to allocate the resource immediately or whether the process has to wait. The disadvantage is lower resource utilization. A resource allocation graph method. It is one of the algorithm of the deadlock avoidance. In resource allocation graph, processes are represented as circles and the resources as squares. A claim edge indicates that a process may request a resource in the future. When the resource is requested, the claim edge becomes a request edge. If allocated, it becomes an assignment edge. If releasing the resources forms a circle in the cycle in the graph, it may lead to deadlock. When a process requests a resource, we check whether converting the request edge into an assignment edge creates a cycle. If no cycle is formed, the system remains safe. If a cycle is formed, the system becomes unsafe and the request must wait. Banker's algorithm. It is a deadlock avoidance algorithm. The name was chosen because the bank never allocate more than the available cash. Each process must claim maximize usage when the process requests a resource it might have to wait. When the process gets all its resources, it might return them in a finite amount of time. Data structures for the Banker's algorithm. Available vector. Let n equal to number of processes, m equal to number of resource type. The vector of table m indicate the number of available resources in each type. If available of j equal to k, then there are k instances of resource type j. Resource type j are available. Next, max. It is an n cross m matrix defines a maximum demand of each process. If max I j equal to k, then process P requests almost k instance of resource type Rj. Allocation. These are n cross m matrix defines the number of resources of each type currently allocated to each process. If allocation of Ij equal to k, then process Pi is currently allocated to k instance of resource type Rj. Need. It is an n cross m matrix indicates the remaining resources made by each processes. If need Ij equal to k, then Pi may need k more instance of resource type Rj to complete its work. Note, need Ij equal to matrix Ij minus allocation Ij. A resource request algorithm for process Pi. When request for resources is made by the process Pi, the following actions are taken. If request I less than or equal to need I, go to the step 2, otherwise raise an error condition since the process has exceeded its maximum claimed. Second point, if request I less than or equal to available, go to the step 3, otherwise Pi must wait since the resource are not available. Step 3. Allocate the requested resources to Pi by modifying the state as follows. Available equal to available minus request. Allocation equal to allocation I minus I plus request I. Need I equal to need I minus request I. If the resulting resources is allocating the state says the transaction is completed and the process Pi is allocated its resources. However, if the new state is unsafe, then Pi must wait for the request I. Example of Banker's algorithm. Let us consider 5 processes P0, P1, P2, P3, P4 and the 3 resources A, B, C. The resource type A has 10 instances, resource B has 5 instances, resource C has 7 instances. This is our example problem. Now we are going to find the need max minus allocation. The process P0 need the value of process P0 need value is 743, P1 122, P2 600, P3 011, P4 431. Now we are going to find out the total allocation using allocation plus request formula. R1 A have 7, B have 2, C have 5. So the total allocation is 7 to 5. Now we are going to find out the available by the formula of total minus allocation. A have the value 3, B have the value 3, C have the value 2. So the available value is 3, 3, 3, 2. Apply Banker's algorithm, search the need matrix from P0 to P4 which is less than the available vector. First we are going to find out the P0 value, but we can't allocate the values because our available value is lesser than the process value. So we going to next we find the P1 value. Now we can allocate because the P1 process value is greater than the available value. So we find the allocation for the process P1 which gives the value 3, 2, 2 and we going to find the available value 2, 1, 0. After the completion of the job P1, it releases the total resources, then the available becomes 5, 3, 2. Then we going to find the P2 value. We can't allocate because the P2 process value is greater than the available value. So we going to find the P3 value which is going to allocate because the P3 value has a lesser than the available value. So we find the P3 allocation value which have the value 2, 2, 2, P3 available 5, 2, 1. After the completion of the job P3, it releases the total resources, then the available can become 7, 4, 3. Next we going to find the value for the P4 which is allocated because the available value is lesser than the process P value, process P4 value. Next we going to find the allocation which have the value 4, 3, 3. Available value, next we going to find the available value 3, 1, 2. After the completion of the job P4, it releases the total resources, then the available can become 7, 4, 5. Next we going to find the, which are the not finding before, now we going to find out that P0, process P0, now we can allocate the values because the P0 value is lesser than the available value. So we find the allocation value which gives the value 7, 5, 3. Next we going to find the available value which gives the value 0, 0, 2. After the completion of process P0, it returns the available value 7, 5, 5. Next we going to find the P2 value. Next we going to find the allocation for the P2 value 9, 0, 2. Next we going to find the available value 1, 5, 5. After the completion of P2, it returns the available vector 10, 5, 7. Executing this algorithm shows the sequence P1, P3, P4, P0, P2 satisfies the safety requirements. The request for the 3, 3, 0 by P4 can't be granted since the resources are not available. Request for the 0, 2, 0 by the process P0 can't be granted since the resulting state is unsafe. Deadlock avoidance ensures that the system never enters the deadlock state. It works by maintaining the system in a safe state at all the times. Understanding the resource allocation graph and Banker's algorithm is essential in operating system. Thank you for watching.